Okay guys, in the last one we talked about magnetic fields and how we can determine the direction of these magnetic fields. In this one here we're going to talk about magnetic fields and charged particles. So how charged particles move within these fields. Long story short, uniform circular motion. But in order to get to the gist of it, what we're going to do is start off with the right hand rule. So right hand rule. Your thumb points in the direction of conventional current, fingers point in the direction of the field, and the magnetic force, comes out of the palm of your hand. So in this case here, my thumb would point to the right because it's a positive charge, direction of conventional current, fingers pointing into the board, and the force is upwards. So with your viewpoint, it might look different because I have to flip this thingy around, but in reality what happens is my charged particle comes in and it experiences a force. As soon as it enters the field, it experiences a little force upwards. So we can do the tangential bit, and then that part experiences a force upwards, and then we can, towards the centre of rotation. So we end up with this kind of curved particle. Now if I make my charge bigger, it'll interact with the field more. So we can possibly have it do these ones. If I make it go a little bit faster, it might do that. If I make it uncharged entirely, it'll go straight through. My question to you, what happens if I make that a negative charge? Alright, the way we can determine the size of the forces acting on these things is these two equations here. F equals BIL sine theta, F equals QVB sine theta. So if we're looking at a single charge, we have a charge is Q. So we're going to use the F equals QVB sine theta. Almost always will be at right angles, so sine theta will turn into 1, so we're just looking at F equals QVB. Alright, so that's for a single point charge or a single chunk of charge. If we look at a current carrying element, so a wire with a current going through it in this field here, it's ever so slightly different. So what I'm going to do now is, let's go this one. Actually I'll extend the field a little bit, so hopefully it will look a little bit easier to follow. I'm going to have now a piece of wire through the centre here, and my conventional current is going to the right. So every single bit of that current that is inside the field, so from say there to about there, that part of the wire there is going to experience a force. A current flowing is in fact a moving charge. So all of these individual moving charges inside that wire, they're all going to experience the force. And instead of being able to move in a circle, it's a line, it's not going to go in a circle, each of these experiences a force upwards. So this wire would attempt to shift upwards like this. This is a really handy thing to know if you're an electrician or you're laying massive big electrical cables with huge amounts of current flowing through them, because as soon as we make the current bigger, F equals BIL sine theta, if we make the current nice and big and the length of thing long, then we're going to have a reasonably significant force acting on it. Sometimes that force is enough to make things lift, move, shift, whatever it is. You're laying a cable under the ocean and it's carrying huge amounts of current through it, and it's really, really long, and it's near the Earth's or in the Earth's magnetic field. You don't want the thing having a buoyant force floating through the ocean. That wouldn't be a good time at all. This force here is perpendicular to the motion, which means that we end up with uniform circular motion. It's perpendicular to the velocity at every given point. So we have something that's perpendicular. We have something that is constant. A constant force perpendicular to the motion is uniform circular motion. It's kind of like, it is a centripetal force. So if it's perpendicular and it's constant, it's a centripetal force. It causes uniform circular motion, which is why these charges go in circles. There's 3 derivations in this section of the course you may be asked to do in the exam, or do definitely in the test. Maybe not all of them though. What you need to do is unpack what's going on. So I'm going to pick the middle one here, so this guy here. So this one here would be the period of oscillation for a charged particle and a cyclotron. So what you need to do is look at what's actually going on. So it's a cyclotron. Cyclotrons have uniform magnetic fields like this. Remember, they have uniform magnetic fields inside what's called the D's, because if you tip your head on the side it looks like capital D's. Inside the cyclotron we have a uniform magnetic field. So mag field, which means uniform circular motion. So if we know that this is a thing that's going to make uniform circular motion happen, we can go back to the equations from the motion part of the course, and we can use V equals 2 pi r on t. So here's an expression we can use that's got a capital T in it, hint, that for this part of the course. If we're looking at other bits that we can put in here, we can actually use this guy and rearrange it a bit. So I'm going to rearrange this first equation here and get V, speed, on its own. This is the radial orbit of a charged particle inside one of these cyclotrons, so we can definitely use this equation. R cubed B on M. So now we've got our expression that's got T in it, it's got some R's, some Q's and B's in it. I'm going to get rid of that because the speeds cancel out. Speed is now irrelevant. So now I can rearrange it. So therefore T is going to go up the top, RQB is going to come down the bottom, and M is going to go up there. 2 pi RM on RQB. We simplify by cancelling, and then we end up with 2 pi M on QB, which is, let's face it, one step, I guess, 2 steps. So we've done 2 things here. That's not worth 3 marks. The thing that's worth 3 marks is this stuff, is explaining how you got the start point. So when you're looking at this one here, yeah, it's for the circular motion of things in a cyclotron. What you need to do is look at forces or speeds or energies that are giving you these scenarios. Link those 2 ideas together. Alright, so with this one here, we've got, it's the period of orbit, period of oscillation, rotation, or whatever, for something in a cyclotron. Things in cyclotrons go in circles. So we can use that period of rotation, circular motion idea in this specific case, and then put some things together, and here it comes out. But we need that link, we need that explanation at the start, otherwise we're only getting 2 marks out of 3. We need to show that level of physics understanding rather than just being able to spit out some algebra. Alright? Thanks.